Hello, today we will demonstrate our new switch-level GDS oversampling functionality using an IGBT leg inverter. GDS oversampling, or gate drive signal oversampling, is a functionality within Typhoon Hill software that enables the Hill device to sample the converter digital inputs with much larger frequency than the time step frequency. This feature provides a great benefit of decreasing the sampling error. Until now, only global GDS oversampling could be enabled, which means that compensation for sampling error is done at the standard processing core level. With the new approach, GDS oversampling is applied to every switch separately. Switch-level GDS oversampling can be very useful in applications which have a high switching frequency and where more than one GDS transition can happen during one simulation step. Because of this, by using switch-level GDS oversampling, we can simulate dual active bridge and resonant converter applications at much higher frequencies. In order to enable this functionality, first we must make sure that we have the right configuration on our device. In the device configuration table, first check which configuration offers switch-level GDS oversampling. For Hill 404 devices, configuration 3 enables switch-level GDS oversampling, so for this demonstration we will switch to the third configuration. This functionality is implemented into the already existing IGBT leg component. To enable it, simply drag and drop the IGBT leg component, choose the Advanced tab and change the oversampling setting to switch-level GDS oversampling. Here we demonstrate our switch-level GDS oversampling functionality on the isolated dual active bridge model, which has a 200 kHz switching frequency. This model has 4 IGBT leg components, all of which have their oversampling settings to switch-level oversampling. In the intermediate circuit, the inductor, resistor, and ideal transformer are connected, completing the isolated dual active bridge topology. The control algorithm is set to phase shift modulation, and the model will be simulated on a Hill 404 with a 250 nanosecond simulation time step. In the SCADA panel, we apply different phase angles between the first and second half bridge carrier signals. In scope, you can see the current that goes through the dual active bridge converter, as well as the voltage waveforms on the primary and secondary winding of the transformer. You can see how the output voltage changes when the phase shift is changed. When we switch to capture mode, we can take a closer look into the signal waveforms and values. First, let's take a closer look into the voltage measurement of the primary of the transformer. You can see that the length of one period of voltage on the primary is 5 microseconds, which means that the switching frequency is 200 kHz. Also, by observing the current that goes through the primary of the transformer, the current waveform behaves as expected for a dual active bridge application. We can see that by changing the phase shift we can alter the voltage waveform and amplitude on the secondary of the transformer, and the output voltage as well. To summarize, this new feature enables our users to utilize the maximum from our devices and to simulate dual active bridge and resonant converters with a much larger switching frequency. This ability was showcased on an isolated dual active bridge with a 200 kHz switching frequency. Thank you for your attention.